we've been working with 2D materials for a while, and we see a very significant level of interest in studying their electronic properties specifically. And we wanted to dedicate some time and speak about how the exabyte platform can be used to design 2D materials, which is a non-trivial task in the first place, and calculate the electronic properties. So today, Brandon is going to focus on exactly that. And without further ado, Brandon, the floor is yours. Please continue.
Thanks, Tamar. I seem to not be able to start my video.
Start the video. 1 second. 1 second. Let me give you the permission. How about now?
Yes.
Great.
Thank you.
Great.
Hi, everybody. Okay, great. So yeah, thanks, Tamar, for the introduction. So the goal of today's seminar is we are going to be, I want to get users familiar with the exabyte platform, using it as a sort of one-stop shop for materials design and computation. I know personally, when doing research on materials, we oftentimes have to use many different computational software tools for our task, such as using one software tool for materials design, 1 or 2 software tools for actually computing properties of our systems, and then maybe another software tool for doing the analysis. I hope to show you today that the exabyte platform consolidates all of these components in an easy to use platform for users. So we'll be using the platform to build heterostructures that contain 2D materials, and we'll be creating custom workflows to compute some of the properties. So specifically, we'll be making 4 heterostructure materials, plus a bonus material, which I'll be sending as a take-home assignment. We're going to create a custom workflow, and then we'll be computing and analyzing properties of these materials. So before we begin, every participant should be a registered exabyte-io user. So if you're not registered now, please go register after the seminar. It's quick and easy. And every participant will receive this presentation in PDF format. And the webinar is also being recorded and will be made available online. So if you happen to have any questions you want to ask, please ask them in the chat. I'll be more than happy to get to them at the end of the webinar. So just going over today's agenda, I'm going to briefly introduce 2D materials, why they're important, their potential applications.
Sorry,
yes?
Sorry to interrupt.
Sure.
I think while I changed the host, the recording also stopped. Yeah, I'm trying to record now, and you should get a pop-up on your end.
Okay.
Sorry for the commotion.
No problem. Are we good to go?
Do you see a pop-up on your end?
I don't see a pop-up.
Okay.
It looks like the recording is going. So I have options to stop it. Yeah.
Okay. Can you assign me as a co-host? I think I've given up the permission there.
Sure. How do I exactly do that?
If you click on the team, on the participants.
Okay.
And under my name, there should be
Make co-host.
Yep. Great.
Okay.
Yep. The recording is going. Please continue. Sorry about that.
Oh, no problem. So what are 2D materials and why are they promising? I'll just skip to this slide. So 2D materials are basically single layer crystal structures that lack a third spatial dimension. So as we know, crystals have 3 dimensions. And if you take away one of those spatial dimensions, you're going to essentially get a 2D material. Now, I think the most famous 2D material is graphene. This is this kind of category that's 1 atom thick. Also in this category is hexagonal boron nitride. I show this on the left here. You can also have 2D materials or monolayers that are 3 atoms thick, such as the transition metal dichalcogenide, like I show here, molybdenum sulfide. The reason why I show this is because I've seen time and time again a confusion if a monolayer can contain more than or be more than 1 atom thick. And so it definitely can. It just depends on the material class. And so the thing that makes 2D materials interesting is that it turns out that this dimensionality reduction brings about new properties that aren't present in the bulk. So for example, like molybdenum sulfide here, as you reduce the dimensionality, you'll notice that the indirect band gap present in the bulk becomes a direct band gap. And also what happens is as you go from the bulk to the monolayer, you're altering the surface to volume ratio, which ends up affecting the optical absorption of the material. Also, as you know, graphene, has an enhanced tensile strength and charge mobility. For example, the enhanced tensile strength is said to be greater than 100 times greater than that of steel, which is quite incredible. And finally, there's a large space you can explore of actually combining these 2D materials to make a heterostructure. And it turns out that these heterostructures have quite novel properties. So for example, molybdenum sulfide and tungsten sulfide, both of these layers can absorb photons. And then what happens is the excitons or the electron hole pairs are able to spatially delocalize over the material. And this affords long-lived excited states in these materials. And so with these properties, you can see how 2D materials can integrate and improve into many existing applications. And when you're able to do such a thing, you're going to be able to innovate, disrupt, and improve various industries. And so this is sort of the hype around 2D materials. And so have we really seen this, though, happen yet? And I would say that not quite. Here is a chart I like of cell efficiency, photovoltaic cell efficiency versus the year. And you could see for the past 45, 50 years, we have done quite well in improving photovoltaic cells. Particularly, I'd like to draw your attention to this region, where we do see some unusually steep trajectories and improvement. And I like to think of this region here as when we've also started having widespread computation, so materials modeling. And it seems like we are making good improvements. But I think overall, we can always improve photovoltaic cell efficiency, especially relative to now. And we still have a lot of work to do. And one thing that's actually hindering our ability to do this is the fact that these systems are inherently pretty complicated. So I show here on the right a schematic of a photovoltaic cell. This happens to be dye sensitized. And you can see there's just so many competing processes, so many phenomena between materials happening that this is just an intrinsically complicated system. So for example, you have photoexcitation occurring on the dye, whose energy level is relative to the surface. And this happens to affect the charge injection. And then the surface bulk interaction has a certain band bending associated with it, which ultimately will affect the charge carrier diffusion into the bulk and then subsequently into the circuit. So if you want to truly be able to improve these materials, you have to understand them. And it's difficult to understand these materials because there's detailed atomistic processes and things occurring, such as this band bending here between this bulk and surface that you have to understand. Now, how would you go about taking known materials and designing a bulk surface or designing any interface to optimize this process here? And I would say you would go onto the materials discovery journey or materials design process, where traditionally it would start with conceiving or synthesizing some new material. You would then characterize and test it, integrate it into an existing application like a photovoltaic cell, and eventually hope to go into product development. But what typically happens is somewhere along this process, something goes wrong and you have to start again. And using just traditional experimental techniques, this can become quite exhausting, inefficient, and expensive. And this is how computation can give you an advantage, because these quantum calculations can give you these atomistic insights into these interfaces and into these materials. And the exabyte-io platform is an easy to use computational engine or platform. I like to think of it as a one-stop shop for materials modeling, where you can actually design your materials, compute the properties, and analyze your results in one sort of easy to use platform. And I hope to show you how we can do that today. And the example I'll be using are heterostructures that contain 2D materials. So just a quick example of like what is a heterostructure? A heterostructure is essentially, very simply, an interface between two different materials. It can said to be made when you bring two distinct materials together to form a new system. And in order to properly describe this new system, you have to be able to properly describe the interface. So this is sort of the regime of heterostructure. So example of a heterostructure with 2D materials. Here I show an example of a monolayer of molybdenum sulfide interfaced with a monolayer of tungsten selenide. Okay, and as I alluded to earlier, these heterostructures have unique properties. So for example, you can have photoexcitation occurring on both sides. So you have a photoexcitation on molybdenum sulfide, photoexcitation on tungsten selenide, and you can see due to the band alignment that the holes on the molybdenum sulfide can relax across the interface to the tungsten selenide, whereas the electrons on the tungsten selenide can relax to the molybdenum sulfide. And in this way, you can spatially delocalize electrons and holes, which is favorable for photovoltaic applications. So in any case, if you're interested in studying these, especially computationally, you're basically going to ask yourself, how can we make these models? And what challenges might we face along the way? Especially if you're newer into this sort of game, this is definitely a step that might take you quite a bit of time. So I think the first issue you're going to run into is this issue of lattice mismatch. So let's say you had a bank of raw 2D materials and you wanted to make an interface. So in this case, we're going to, our desired heterostructure would be this interface between graphene and molybdenum sulfide. Well, the problem is that our computational models have to be finite because we have finite resources and we're using density functional theory, which is quite a rigorous level of theory. And it turns out our systems have to be a finite size. They can't just be infinite. So you have to worry about this lattice mismatch. And for example, you can see the lattice constant of molybdenum sulfide is not able to just directly superimpose onto the lattice constant of graphene. Okay, you have quite a significant mismatch here. So what you have to do is figure out a way to manipulate the system such that the manipulated unit cells will be able to be brought together. And this brings me to the concept of root integer supercells. It's something I'd like to just introduce to you all. If you have more questions about this or want to talk later, I definitely would be more than happy to. So just for example, let's say you had molybdenum sulfide and graphene, and you wanted to make a heterostructure. You wouldn't be able to just simply superimpose these systems onto each other because of the mismatch in the lattice constant here. So what you'd have to do is find compatible lattices. So one thing you would do here is obviously the 1x1 cells aren't going to work. So you would consider like a 2x2 cell of molybdenum sulfide, and that would bring you to a lattice constant of about 6.32. And then what you would do is take your lattice of graphene. Here I have the 3 lattice vectors. If you're used to using the VASP simulation engine or Quantum Espresso, you might notice in your POSCAR file, this matrix at the top, that's essentially these 3 lattice vectors. What you end up doing eventually is you find some matrix P that when taken with your lattice vectors, give you a new set of lattice vectors, where the magnitude, for example, of this A lattice vector is as close as possible to the target molybdenum supercell. And it turns out here that you can find this matrix P. It's a complicated process that's quite mathematical, and it's definitely a topic for another discussion. But for example, this particular P, which I happen to find, was able to give new lattice vectors. And you can see that the magnitude of these lattice vectors are actually very close to that of molybdenum sulfide. So here's a visual example. This might help better explain. Here I show graphene with its original lattice constant, and that's these black lines here. So after I apply this rotation, this matrix to these lattice vectors, you can see how it actually rotates the cell a certain amount. In this case, it's 19.1 degrees. And then it actually expands the lattice constant by √7. And you get this red cell here. So, and this is after the transformation. So basically this √7 supercell means that the new supercell I have has a lattice constant that's √7 times larger than the original lattice constant. So that's what they mean by these root integer supercells. I don't think this is covered enough. And it is often a point of confusion some people have. So today, with this in mind, we're going to make 4 heterostructure systems where each one contains a 2D material. The first one we're going to make is between molybdenum sulfide and tungsten sulfide. This one's going to be trivial because we're just actually going to be able to superimpose the 2 systems together. They have a very similar lattice constant. This one is ranked medium in difficulty because you actually have to scale both lattice constants. Here we don't use the root integer supercell. We actually just use integer supercells of each system. Here for this this interface between hexagonal boron nitride and molybdenum sulfide, we are going to use some root integer, and we're going to need transformation matrices. And this is very difficult because actually the interface is not between 2 hexagonal lattices. It's actually between a hexagonal lattice and a cubic lattice. The perovskite here takes the cubic lattice. So the first thing we're going to have to do is to make these heterostructures using the exabyte platform is we're going to have to upload our raw materials to our exabyte-io material set. So here's how we do this. We're going to be beginning in the exabyte entry gateway, and we're going to go to materials. And here I'm clicking on the August webinar material set. And what you'll find here is that you could be able to create a set if you wanted to. Here, I'm just going to go ahead and click the upload button because I'm going to upload POSCAR files or VAS files from my desktop. So here I go to select items. And you can see here that I'm in this raw materials folder I made on my computer. And I'm just going to go ahead and select each of these files. Then I'm going to select open. And you can see here, we've loaded these systems onto the platform. I then select them and then go to upload. Sometimes this may take a second if we're uploading various materials. You'll be able to know that they're uploaded when you see a check mark appearing, as you will soon. And then finally, once they're all uploaded, you should get a notice that the upload was successful. Okay, so now we can exit out and go back to our material set where you see our uploaded systems. Let's go ahead and click on tungsten sulfide. This brings us into the material. Here we can toggle the material and you can see. Now, let me just take you back to show you what this does. Brings you back to the materials folder. We can click on the material set and you can see the materials that we just uploaded. Okay, now, finally, before we begin, I'm just going to give you a brief overview of the materials modeler. So again, beginning in the entry gateway, we're going to click on the top left and go to materials. This brings us to our materials folder where we click on our material set. If you haven't made this specific material set, it won't be there, so you can go ahead and make it. We're then going to click the create button. So when we click this create button, what this is going to do is it's going to bring us into the material designer where you should see your default material. So sometimes this does take a second. Okay, so here we can see our default material, which in this case is aluminum oxide. We also see in the middle two things. We see crystal basis and crystal lattice. This crystal basis contains the atomic coordinates, both in crystal units and in Cartesian units. Okay, so anytime you want to manipulate these, you can just do this down here. We also have crystal lattice, which contains information about the lattice, such as its units, its types, as well as the vectors, such as their magnitude and the angle between them. So we can also toggle the material by going to interactive view in 3D. Okay, I right click to drag and left click to swivel. So this is how I'm actually viewing this material. To toggle the bonds here, I just want to show you, you can click this toggle bonds and it'll bring up the bonds between the atoms. Now let's make a supercell by going to advanced supercell. Here, I just want to expand it 2 by 2 in the X and Y dimension. I then press submit. And you can see how simple it is to make this supercell here. Now, at any time, if you want to actually undo something you've done, you could just go to edit and click undo. Now, one of the last things here I want to show you is how to make a slab. So let's go back to the advanced and go down to surface slab. We're going to go to change this Miller index from H to L. So this will add vacuum in the C dimension. For thickness and layers, we're going to actually change this from 3 to 1. We don't want to add any extra layers. This vacuum ratio basically means our new cell will be 80% vacuum. And I'm going to have the X and Y dimensions be expanded 2 by 2. So clicking submit here should take me to our supercell. Okay. And you can see this nice supercell here. So how do we actually put something on top of this? So what we're going to do is we're going to go to input and we're going to import. Okay. This will bring us back to the materials folder, which should then bring us back to the raw materials we had uploaded. So we clicked our material set, and now I'm going to click molybdenum sulfide. Okay. Apologize for any delays here. And then I'm going to go to select items. And you can see now the molybdenum sulfide has been imported into our material designer. So now what's going to happen is we are going to have to place this molybdenum sulfide into the aluminum oxide. So basically whatever material is at the top here, this is the material that's going to be the parent lattice for the supercell. And we combine the materials by going to view material editor. So we're going to place the molybdenum sulfide into this parent lattice. So we do this by going to view multi-material editor. So here you can see the two materials, and right now they're just sort of superimposed on each other. So we can go ahead and rotate around, view our materials, but how do we actually separate them? So we use this panel on the right. You can see camera, scene, new material, and atoms. When we click this first atoms, it's going to click the atoms belonging to the parent material. Here I can scroll down and you can see all those atoms. I can toggle the axes here to shift the material. And if I want to switch to the other material, I can scroll down until I see it in the set. So here I select molybdenum sulfide, and I can toggle this as well. Okay. Now I can also do a rotation here. You can see by clicking at the bottom. And I can also do the scale option, which is pretty cool. So now I'm going to go back here, and I'm actually going to try to rotate this back, and then I'm going to translate it to the center of the cell. Here, this is quite a silly heterostructure, but it's just for demonstration purposes. We'll make real heterostructures in a second. So here I've decided I want to place my molybdenum sulfide above my aluminum oxide. Okay. So once you're satisfied with your heterostructure, you can go ahead and go to File and go to Exit. And you should see your new material pop up here. And you can look at the formula underneath new material and see that it is indeed the combined cell. So now what I can do is I just like to rename these new materials. So here I just call it new system. And to save it, I go to Input, Output, Save. Now, just in this example, I'm going to show you where it actually saves to. So we go back to the materials folder, or account materials folder in our account profile. And I'm going to click on the August webinar set. And you should see our new material is now saved in here. And finally toggling it, you can see the material we just made. Okay, so keeping these things in mind, let's go ahead and begin to build our heterostructures for today. So the first one we're going to build is molybdenum sulfide and tungsten sulfide. Now, this is just trivial because the lattice constants are so similar. We can actually just superimpose and take the average here. So let's go ahead and do this. So beginning in our materials designer, we are going to go to Input, Output, and import our materials. This will bring us back to our materials folder where we select the August webinar materials set. And we're going to then select tungsten sulfide and molybdenum sulfide. And we are then going to import it. Oops. Okay, so we can delete the default material, and now you see the two materials we want. So now what we can do is we're going to make our monolayer. So how I'm going to make this monolayer is I'm actually going to delete the bottom layer directly in the crystal basis editor. Okay, and now what we're going to do is we need to add vacuum. I can go to Advanced Surface Slab. And what I'm going to do is change the Miller index where the vacuum will be. I'm going to keep the thickness in layers to 1, and I'm going to change the vacuum ratio, then submit. You can see now we've added sufficient vacuum into our system. Now I'm going to do a similar process for molybdenum sulfide, but here I'm going to actually delete the top layer. And now just to show you again, I'm going to go back to Surface Slab and I'm going to add vacuum. You don't actually have to add the vacuum in this step here, since we use since the cell we use for the heterostructure is in the tungsten. So now let's go in to our multi-material editor. So all I'm going to do here is I am going to actually just move in the molybdenum slab so that it stacks in the same way that the original upper slab in tungsten selenide was. This is a particular stacking pattern. And to judge the interlayer distance, I'm just going to visualize that original unit cell of either tungsten selenide or tungsten sulfide and molybdenum sulfide. So I always try to use the edges of the axes as a guide to help move these. And after you do these, it is recommended to do a geometry relaxation. So here I move it up just a little more, and I envision that original unit cell. Once you're satisfied, you can go to File, Exit, and you can see your new material. So what I'm going to do is rename this new material. We'll call it something like molybdenum sulfide, tungsten sulfide. And one thing I do want to do is actually change the lattice here, because this is the lattice of the tungsten. So what I'm going to do is actually take the average, which is about 3.175. And this actually will directly affect all the atoms in the cell, because the atoms in the cell are stored here in direct coordinates. So once I'm satisfied, I can go ahead and save this. So we've just made our first heterostructure here. Okay. So our second one now, what we're going to do is we're going to make a heterostructure between a molybdenum sulfide monolayer and graphene. So we're going to expand the molybdenum sulfide 4x4 and extend the graphene 5x5, and then sandwich them together in a similar way. So beginning in the materials designer, we're going to go to input output and import our materials. This will again bring us to the material set, August webinar, where we will then select from our raw materials that we uploaded earlier. We can delete the default material. Okay, just like we did last time, we're going to make our molybdenum sulfide monolayer. And now we're going to actually make a supercell slab, a surface slab that is extended in the XY dimension. So here we're going to change the Miller index, set our thickness layer in layers to 1, choose an appropriate vacuum ratio. And now we're going to set this to 4x4 and click submit. So now you can see we have a 4x4 slab of molybdenum sulfide in the XY dimension, plus some vacuum. And notice the lattice constant here. So what we're going to have to end up doing is stretching the graphene here to fit the molybdenum sulfide. So now what we're going to do now is just simply make a supercell of graphene. We're going to make it 5x5. And now what we're going to do is actually stretch this lattice. You don't have to stretch it. You can use this, but it would make the lattice strain be sort of localized at one point, which might make geometry relaxation harder. So by stretching it in this way, you sort of delocalize the strain a little bit. So going into our multi-material editor, now what I'm going to try to do is simply use the edge of the unit cell as a way to place the graphene atom. So I scroll down and I'll select the graphene system, and I'll simply just translate it into the cell, using the edge of the supercell as a guide. So when I'm trying to figure out the interlayer distance, this can be quite challenging. What I like to do is envision space filling models of the material, and I try to think about where they might be. So I'm satisfied here, and I'll go to exit, click on my new material, toggle the bonds, and you can see this nice interface we just made. So you might notice it looks like some atoms are missing. This is because the viewer takes into account periodic boundary conditions. So renaming this graphene molybdenum sulfide, and then going to save. Okay, and this should be saved to our material set. Okay, now let's go into something a little more interesting. We're going to make an interface between molybdenum sulfide and hexagonal boron nitride. To do this, we're going to have to make a 2√7 by 2√7 hexagonal boron nitride surface. So again, beginning in our materials designer, we're going to have to import our materials. What we're going to do here is we're actually going to import the hexagonal boron nitride first, because this cell is the cell we're going to want to use to be the cell of our new heterostructure. So we want this material to be up top in the materials designer. Okay, then what we're going to do is import our molybdenum sulfide. Okay, so we have to make a sheet of hexagonal boron nitride. I'll do this by deleting the bottom layer. And now we're going to have to apply the transformation. So here I'm going to make the √7 cell. And you can see here, this has transformed the cell. So now what we're going to do is we're going to have to make it 2√7 by 2√7 and add vacuum. I do this by going to Advanced Surface Slab. I keep the thickness and layers to 1, add an appropriate vacuum ratio. And now I just make this 2 by 2. Click submit. So now I have my 2√7 hexagonal boron nitride cell. And you can tell the lattice constants now. We have to keep these in mind. So going to molybdenum, I'm going to do the procedure we've done for the last two systems and make the monolayer. And then what I'm going to do is simply just make the supercell here. Once we're done, we can click submit. And now you can see our 4x4 slab of molybdenum sulfide. Molybdenum sulfide. So now I'm just going to stretch the molybdenum sulfide. This is quite a big stretch, but I'm just going by what the paper was. So now what we can do is go to our multi-material editor. And I wanted to show this particular version of hexagonal boron nitride, so I can show you using a rotation in the editor. So I go down and select the molybdenum supercell. I go to rotate, and I'm just going to rotate it so it's sort of the cell, so it's easy to translate into the cell. So once I'm satisfied with this, I'm now going to go back to the translate option and move it into the cell. Again, when I do this, I'm using the edges of the unit cell as a guide to placing it in. So here I'm going to have the molybdenum be on this side of the unit cell, the supercell. And now I'm just going to translate it in, having the sulfur be on this edge. So I consider placing the molybdenum sulfide below, but I end up opting to place it above. If you always want to add a little more than I do, you can just simply move it a little higher. So here I end up being satisfied, and I'll go into eventually save this. Okay, so now I simply am going to check out my new material and then rename it. So this one was slightly non-trivial due to having to make the root integer supercell of hexagonal boron nitride. So I hope you are getting a feel for how this works now. So let's move into our final structure. This one I have as the most difficult because it combines sort of all the concepts we've learned so far. So we're going to have to first force a sort of rectangular coordinate system or lattice onto our molybdenum sulfide. So we'll move from a hexagonal lattice to orthorhombic lattice. And then what we're going to do is have our cesium lead iodide. We're going to actually make it 3 layers, 4 layers actually, delete the top layer so that it's properly terminated, and then make a 1x5 slab. So let's go ahead and start. So once we're in the materials designer, we're actually first going to import the perovskite because we want this to be our upper material, which will be the sort of overall lattice for our superstructure. So I go ahead and I click the cesium lead iodide here. Delete the default material. Okay, so now let's go ahead and make that big cell. So I'm going to go to advanced surface slab. And I'm going to put the vacuum in this dimension here by selecting the 1 for Miller L. And thickness and layers I'm going to leave to 4. Okay, I choose an appropriate vacuum ratio. And I'm going to make the X and Y dimensions now 1x5. This is to match what was reported in the paper. So you can see this is quite a sizable system. So yeah, we're going to have to delete that top layer there that I just showed. This is to get the proper termination. Now let's import our molybdenum sulfide. Okay, click the molybdenum sulfide and then select items. So now that we've imported it, we're going to do like we did in the last 3 examples, where we're going to make the molybdenum sulfide monolayer. And now we're going to apply a transformation matrix to switch the sort of lattice system. So this is just a simple transformation here. And you can see now we're in this sort of rectangular orthorhombic frame. So now what we're going to do is make a certain supercell out of this that is compatible with the perovskite system. So I'm going to change the thickness and layers back down to 1, and I'm going to make this 2x6. So this is quite a large system. And you can safely ignore this warning. So now you can see how this is going to be fitting into the perovskite system. Now, one thing I'm going to do is I'm going to have to stretch in some of the lattice vectors. So here we're going to make the molybdenum A constant be a little larger. And then we select apply edits, and we're going to make the B constant a little larger for the perovskite. This does help the geometry relaxation a little bit. So once we've done this sort of transformation, we're now in a position where we can go into our materials editor. And first thing we have to do is delete this top layer of the perovskite. So you can do this by simply clicking the atom and then pressing delete or backspace. And you can see now that there is this large box around the perovskite system. This encompasses all the atoms in the system. One way you'll be able to know that you've successfully deleted the monolayer is if this box shrinks after you delete the last atom. So this is a good guide that you've successfully deleted that top layer. Now what we're going to do is I'm just going to line up that left axis of the supercell relative to my screen. And I'm going to scroll down to molybdenum sulfide. And I am going to move it so it's on that edge. Then I'm simply going to translate it up. So here I'm actually going to consider quite what might look like a large distance between the unit cells. And the reason is because I always think of the space filling model when I decide the interlayer distance initially. And I know that cesium and lead are kind of big atoms. So I'm just imagining that space filling model being kind of large there. Now, finally, I'm just going to add the final touches where I am moving the system to be at the edge of the cell, just for visual, just to help me visualize the system and make a good initial guess. So once you're satisfied with your system, you can go ahead and go to File, Exit. And you can see here that in our new material, we do indeed have the system that the authors made in the paper that I referenced. So, and you can tell that this is just an absolutely massive system. So let's go ahead and rename this material and save it. Okay, so we've made our materials today. By now, I think we are pretty comfortable with using this materials designer. So now what we have to do is we have to actually make a workflow to be able to compute some properties of these materials. So the workflow we're going to make today is going to be one that does a geometry relaxation, followed by a band structure calculation, followed by analysis of the electrostatic potential energy profile. So to do this, we have to make a sequence of execution units. So, and we're going to be using the Quantum Espresso program. So the first execution unit we're going to make utilizes the pw.x executable. So in this step, you have for this executable, you have various flavors you can choose from. I'll show you this in a second. So at this step, you could use any of these three flavors. You could use the VC relax. If you end up using this option, I would suggest you only relax the XY components, because if you relax the Z component, the periodic image of the slab in the Z direction might actually come down. If you're confident of your lattice, you can just do PW relax, which will just change the atomic coordinates and not the lattice. And if you happen to already have a relaxed geometry, you could do just a simple single point calculation here. So now what we're going to do is go to the band structure calculation, which contains the pw.x executable with the pw bands flavor, and then the bands.x executable. Following that, we're going to do a little sequence that allows us to analyze the electrostatic potential energy profile using the pp.x executable. This PP stands for post-processing, and we're going to be using the electrostatic potential flavor. Now, this is in development still and will be available in the next release of the exabyte platform. And following that, we're going to do the average.x executable. And then finally, I have a Python script for additional post-processing. Now, using this information, we're going to be able to compute things such as band offsets. So here, for example, is a very nice picture in the literature I found, where you're able, so for this system here, they actually were able to compute the valence band offset using what's known as the potential lineup method. So what they've done is they've done individual calculations on this strontium, titanium oxide perovskite, and titanium oxide. And you can get the valence bands of each system, right, quite straightforwardly. But the problem is you can't just compute the difference of these, because these values are actually in reference to something different for each system. So what you do is you reference them to the macroscopically averaged electrostatic potential energy. And so in this case, they take the difference between these two and then reference that to the difference between the macroscopically averaged potential across the system. And in this way, you're able to compute valence band offset. Now, there are some cases where just taking the difference of these energies ends up giving you a good approximation to the valence band offset as well. So to do this, we're going to have to create a new workflow. So to create a new workflow, let's go to the exabyte entry gateway, and we're going to go to the top left, and we're going to go to workflows. So here I am in a demo account now, because this is a new feature. So let's go to create. This will allow us to create a new workflow. The first thing I'm going to do is rename the workflow, such as relax plus band structure plus electrostatic potential. I go ahead and name the first sub workflow here the same thing, relax plus band structure plus electrostatic potential. So now it's time to add those execution units. Okay, the first unit I'm going to add is going to be a relax calculation. It's going to have the pw.x executable, and the flavor could be pw relax, or if you wanted to do variable cell relaxation, it could be variable cell relax. Here I just choose relax for demonstration purposes. Now we're going to add another execution unit. Here will be the first part of the band structure calculation. It uses a pw.x executable with a pw bands flavor. And just to check that these are actually working, you can scroll down and see that the calculation is in fact for bands. Okay, so what I'm now going to do is exit out, and we're going to have to now do our bands.x executable. So here we change the executable from pw.x to bands.x. And you don't have to worry about selecting a flavor here for now because they're just a single flavor. Now let's go into computing the electrostatic potential. So here we have to change the executable from pw.x to pp.x. Again, pp standing for post-processing. Here I change the flavor from density to electrostatic potential. Now what we're going to do is add the average.x executable. This is just another post-processing on the electrostatic potential profile that was made in the previous execution unit. And then finally, what I'm going to do is add an additional sub workflow with this plus button for extra Python plotting I wanted to do. And these scripts will be made available to you. So I'm going to change the application engine from Quantum Espresso to Python. Then I'm going to add a new unit. And so this unit here, all you have to do is scroll down and replace the default Python with the script I have here. Okay, so we've now made our new workflow. So you can go ahead and save by pressing the checkbox. And you can now see our new workflow has been saved in our workflows tab of the account profile. Okay, so now let's actually compute the properties. We've made our system, we've made our workflow. Let's now make our job. So starting in the entry gateway, you're going to go to the upper left-hand panel and you're going to go to create job. So here's where we can bind everything to the actual job. So first thing I do is I'm going to name the job. I'll name it molybdenum sulfide, tungsten sulfide, job number 1. Now let's select our material. So we're going to select that first heterostructure system we made. And you can see in the materials editor here, you can see this is indeed the system we made. Now let's go ahead and select our workflow. This will be the workflow we just made. So you can see here I have a relax plus band structure, electrostatic potential. Now it's time to actually set the parameters in our workflow that are specific to our calculation. So here I show you we have the wave function cutoff, the charge density cutoff, which I make 12 times because I'm using ultra soft pseudopotentials. I choose a modest K-point grid here. This is ultimately for demonstration purposes, so you would need to choose this based on a convergence criteria. And you could see here, this is something I really like about the exabyte platform, is you can see it already shows you the reciprocal lattice and maps you a route through it. Okay, and here is the path in reciprocal space we will walk for the band structure calculations. It also tells you how many steps between each high symmetry point we're going to take. You can press this X button to remove a high symmetry point and plus to re-add it back. Okay, so here I'm satisfied with this path. What I'm now going to do is go back to the overview. And we do have to do one important thing here. We're going to go to the average.x executable, and we're going to change the window size for the macroscopic averaging. Here I choose 5.7. This unit is in unit of Bohr, and it corresponds to the distance between the sulfur atoms in like MoS2 or tungsten S2. Okay. So now once you're satisfied, you can then scroll back up and go to the compute tab. Here, you're going to have to set this based on your own specifications. This is just a demo account, so I'll leave this as it is for now. Once you've saved your job, you can go ahead and go to the right and go to run. And this will actually submit your job to the platform for computation. Okay, so let's now look at our results. So following the calculation, you're going to be able to obtain your results. And so what I did was I took away the tungsten sulfide in one case, I took away the molybdenum sulfide in one case, and then I had the combined system. So on the left here, I have just a monolayer of tungsten sulfide using the exact same workflow we made. You could see here's the band structure calculation. It shows a very nice direct band gap here at one of the K points. It shows here the planar averaged in blue and the macroscopically averaged potential energy profile. Now, if you're used to these type of plots, you might be used to them for bulk calculations in which you would see this macroscopic average would be sort of a flat line through the bulk system. But because we just have a monolayer, it's just going to be relatively flat at this point here. I do the same thing for molybdenum sulfide, which shows a very similar behavior to tungsten sulfide. And then finally, for the bilayer, which you can see, once we add that second layer back, our direct band gap now reverts to an indirect band gap, as we see in the bulk systems. And here, I have the electrostatic potential energy profile for all three materials. Now, using this formula, we can compute the band offsets. So here I show in the top right, just sort of the band offset picture that you can generate by doing the individual calculations just on like the monolayer. So for example, for a monolayer tungsten sulfide, I would get these as the band edge energies. Same thing for molybdenum sulfide. And like I said before, you can't just take the difference of these two because these two energies are actually referencing different values. So what you do is when you compute the valence band offset, you actually reference them to some property of the electrostatic potential. So here what I do is I take this valence band energy, plug it in here. I take the macroscopically average potential energy profile in the center of my monolayer as this value, and I just plug it into these formula and go ahead and use the difference of the macroscopically average potential across the interface for this term. And doing it this way, I compute a valence band offset of about 0.25 electron volts, which is in good agreement with previous theoretical calculations using, this is another one using the LDA, and this is using the GW approximation. And here, reference 2 is actually experiment. So I think this is pretty good. Here's a schematic from reference 2, just to show the interface. So you can see that we actually have a type 2 band alignment here with a band offset of about half an EV. And this actually looks very similar to what we found in terms of aligning the energies based on the calculations of the individual monolayers. So there's also another way, another thing you compute, such as the Schottky barrier height. And we're going to compute this for graphene and molybdenum sulfide. So you could do this using what's called the effective screening method calculation. This is available in the Exabyte platform. And here's a reference to read about it. I think this is the original paper. So the first thing we're going to have to do is set up our calculation, our effective screening medium calculation using our graphene molybdenum sulfide system. So the first thing we have to do is prepare our structure for this calculation. So what this effective screening medium does, it effectively is going to cut off the periodicity in the vacuum dimension, and instead it's going to flank your system with semi-infinite media. In this case, we're going to use the vacuum slab vacuum model. So the first thing we're going to do is, starting in our account profile materials, is we're going to have to go and create a new material. So here I'm importing graphene molysulfide system that I did a VC relax in the XY dimension already. Okay, so this is an optimized system. And then what I'm going to do here is I'm going to go to advanced, and I'm going to go to boundary conditions. And here's how I set up the calculation. I choose the first boundary condition, vacuum slab vacuum. And you can see there's many different types we can choose from. So you can see here now that our system is vacuum slab vacuum, and then we have these special boundary conditions for the problem. And this is, what you could also do here is you could go into the Cartesian units and you could rigidly shift the system such that the middle of this is sitting between the middle of your interface. So I've now renamed it and saved it. And yeah, this is our new system now that we're going to use for the effective screening medium calculation. So once you've done this, you can go ahead and create the job for the calculation. So this is very similar to what we had before. So here I had submitted this job a little bit ago, and now I want to make another job. So I can go ahead and go to create job. And you can see here that I'm in a new job, and I'm going to name it Graphene MOS2 ESM boundary condition 1 calculation. So the first thing we have to do now is import our new material. So we click on the right here, select material. So now we're going to select that boundary condition 1 material we made. And you can verify the material by looking in the material editor. I would always recommend this step. So now what we're going to do is go to select workflow, and I'm going to search for the effective screening medium calculation. So now what I'm going to do is simply go into our file, and I'm going to do something. I'm going to add van der Waals correction, because between molybdenum sulfide and graphene, you might want to add van der Waals correction. Okay, so this, for example, is how you could add van der Waals correction into your calculation. Final thing I'm going to do is go to important settings, and I'm going to just change the charge density cutoff and the K-point grid. Again, these things you'll have to decide yourself through a convergence study. When you're satisfied with your materials and workflow, you can change the compute tab as you need. Here, I just leave it as it is because I'm in a demo account. And now you can submit your calculation. Okay, so what do we end up getting? Well, so what happens is in the effective screening medium calculation, your main result will be a plot similar to this. And what you see here is I have lined up on top our system, this 4x4 graphene and 3x3 molybdenum sulfide. You can see the potential energy profile here. And one thing I want you to notice is that in these long planar regions, if I take the difference between these two regions, you can actually use this to compute the Schottky barrier height. So I do this here and I get a value of about 0.259, which is in pretty good agreement with previous theoretical calculations and in really good agreement actually with this one experimental result. And this here is another experimental result. So this, I really like this method because it makes this so easy to do. You just do your calculation and then you can find the differences between the two sides and take this to be your Schottky barrier. If you would like to learn more, I gave you the reference in a previous slide. Also, what you can do is go back to making this model and consider just individual layers. So here I consider just an individual 4x4 layer of graphene. I've computed the band structure here. Same as a 3x3 layer of molybdenum sulfide. And you can see here, just one thing I'd like to point out is that the band gap is now at the gamma point for the 3x3 molybdenum sulfide. This actually has to do with band folding in the hexagonal structure. And it turns out to be a special case when you have a 3x3 supercell. Now, for the case of graphene in the effective screening medium calculation, what happens is because the vacuum here is asymptotic to 0, you're able to actually compute the work function quite easily by just taking the negative of the Fermi energy. And so this is the work function I computed of graphene using this method. This calculation was very fast. It was roughly like 7 minutes. And it's in good agreement with some work function values of graphene I found in the literature. I provide a reference here. So in summary, I hope today's talk was helpful. We've learned to use Exabyte's native materials modeler to build 4 heterostructure systems. Each of them was of various difficulty. We built a new workflow from scratch, quite a complicated workflow. And we used it to compute the band offset between molybdenum sulfide and tungsten sulfide. And then I showed you how to set up a model and workflow for the effective screening medium calculation and the results I obtained from that for graphene molybdenum sulfide system. So please join us the 3rd Friday of next month for our next webinar. I'll make these structures available on GitHub for you. And finally, I'd like to leave you with a challenge. So, go on your Exabyte account. If you don't have one, make one and try to make this system based on what we learned today. The slide I had with the root integer supercells should be very helpful because I actually show how you can make this cell here. And then, yeah, let me know how it goes. So thank you so much, everybody.
Great. Thank you, Brandon, for the thoughtful presentation. We have one question that I'd like to answer also verbally here. Joy was asking about whether we support CIF file format instead of WASP, and the answer is yes. So there is a way to use CIF files instead of postcard files when you upload the structures. I don't see any other questions yet in the Q&A, so if you have any other questions right now, use the time to ask. But let me go ahead and ask a question first. So when you have the ESM calculation at the end, you have used the workflow for it that you had under your account. Maybe we can explain to the users how they can import it from the bank as well.
Okay, sure.
Because they might not have it already under their account.
I see. Okay. Should I pull up a copy of Exabyte to show?
Yeah, or maybe just explain it with one of the visuals.
Okay. So what we can do here is I'll go to the, I think, here in Create New Workflow, when you click on this top left button here, you'll end up seeing this bank button here. And when you click this bank button, you're going to see a drop-down that will show you materials and workflows. And if you click on that workflow button, it'll bring you to a searcher where you can then type in effective screening medium or ESM, and you should be able to search the entire bank of workflows and find your desired workflow.
Yeah, we would also advise initially to get the workflow that is created by curator's account, because that is the account that the Exabyte team curates and manages and asserts the quality of the workflows initially. Okay, and maybe we can speak about the average.x or the new upcoming functionality that you briefly mentioned.
Sure, and I do see a question as well. So yeah, the upcoming functionality is going to be new flavors for Quantum Espresso. So in the post-processing executable, currently on the platform now, we have a flavor for computing the charge density, but we're going to be adding a flavor for computing the electrostatic potential. And what this does is the post-processing executable is going to go into the results you've got from your single point calculation, and it's going to use some of those stored files and output to you some parts of the Hamiltonian ultimately, and you'll be able to see the potential energy, the electrostatic potential energy profile. Now, what you have to do after the post-processing flavor is you have to do an additional executable called average.x. This is actually going to be computing the different averages of that electrostatic profile, such as the planar average and the macroscopic average as well.
So that's an upcoming functionality.
Mm-hmm.
We have another question from Chilal. Can you please show again the root supercell creation? They couldn't catch it yet. Let's come back to that part maybe.
Sure. So what I ultimately do is you'll start with two systems, and the lattices, the lattice constants of these systems are quite different. So in the hexagonal system, you have this condition that the A vector should be equal in magnitude to the B vector. And so that's why this is called the lattice constant, because in the 2D material, the C dimension doesn't matter. So you're just looking at this lattice constant here. Okay, anyways, so when you want to combine these two systems, you can't directly combine them because the lattice constants are very different. You'll have an artificially high strain in your system. So what we do here is we say, okay, the 1x1 cell won't work. So let's consider a 2x2 supercell of molybdenum sulfide as our starting point. And that gives us this. So now what we end up finding later, and I found this through the literature, is that people found that the root 7 cell of graphene matches well with this. So how do I make the root 7 cell? So what I do is I take the original lattice of graphene, which can be given by these three vectors. So if you go to the top of your VAST file or POSCAR file, you'll see this matrix, and that happens to be, these happen to be the rows of that matrix. And it just so happens that you could take these vectors and you can also take a certain permutation matrix P, and if you make your matrix P, it turns out that when you apply this operation, you get a new set of vectors such that the magnitude of this A vector or this B vector is as close as it possibly can be to this one. And so, yeah, that's how you make the root 7 cell. And the reason why it's called a root 7 cell is because you can see here in this picture, I take my original graphene unit cell, which has these vectors here, and I apply this P to it through this method here, this equation. And after I do that, I'm actually going to get this new supercell. And this new supercell is simply this original supercell, this original unit cell that's rotated a little bit. And then the lattice is scaled by root 7. So that's why it's called a root 7 supercell, because the new lattice vector after the transformation is root 7 times larger than the original unit cell. And the way you make it is simply by applying this transformation matrix to the original cell of graphene. Was that helpful?
See if Chilal, okay, looks like it was.
Oh, great.
Great, thank you for confirming. We had another question from Joy. Joy was asking about showing the density of states calculations. We don't have the content prepared for today to demonstrate it, but I've referenced a step-by-step tutorial that we have in the documentation. Please let us know if it's, after looking at it, please let us know if you have any other questions. Maybe submit a support request through our portal online, and we'll be happy to assist more. All right, we're running a bit over time. So with that, I think we would like to wrap up today's session. If you have any questions, please contact us at info@exabyte.io. Either myself or Brandon will be able to answer, or submit a support request to the platform if you have any specific questions like the density of states calculations. Thank you very much, Brandon. Thank you, everybody, and we'll see you next month.
Yeah, definitely. Yeah, take care, everybody.